Hi everyone, and welcome to part 4 of this formal logic video series. In this session I'm going to introduce 4 more rules that we can use to construct proofs in PL. So I'm going to look at the making of assumptions and reiterations. I'm going to introduce us to the conditional introduction rule and the biconditional introduction rule. And then I'm going to go through a few examples of those rules in action. To start with, let's look again at the rules we've already covered in previous sessions. Now, when we looked at these rules before, we were only using one scope bar, but it would have been more correct when stating these rules to say that we're justified in writing these formulas, so for instance phi and psi, only if phi and psi appear above that formula on the same scope bar. And a similar thing can be said about each of these. Where a formula is introduced, its justification must appear above it on the same scope bar. Now, with the conditional introduction rule, what we're actually going to do is move to a different scope bar, and the justification for a conditional formula being introduced is going to come from a subproof. So let's take this sequent, B, therefore A, then B. We'll be using the conditional introduction rule in order to get A, then B, but the way that we'll do that is by introducing a second scope bar to the right hand side of the first. Now, our conditional A then B is in other words saying that if A is the case, then B will be the case. And in order to show that, we're going to need 2 little tricks. So the first is that we're going to need to be able to create that hypothetical situation, and we'll do that by making an assumption. So on our second scope bar, our one to the right hand side, we'll begin that with the assumption A, and we'll draw a line under it to show that it's an assumption. Now, we mark our premises with a P, and we'll mark any assumption with an A. So this second scope bar is a subproof, just looking at this hypothetical situation, assuming that A is the case. And now we can see what follows from A being the case. Well, we already know that B, but B is on this primary scope bar, so in order to get it here, what we need to do is reiterate it. So we can write B on this scope bar and justify it with an R here, just to show that it's a reiteration of a previous point, and we'll need to write line 1 there. Okay, but now we have a subproof that shows that assuming A is the case, B will be the case, and that really just is the meaning, or part of the meaning at least, contained within A then B. So this subproof of A to B justifies us in writing on line 4, A then B. And the justification that we'll write here for that is the subproof, so 2 to 3, and conditional introduction. So we always, the subproof might be quite long, so we'll always give a hyphenated range of numbers, 2 to 3, to show that that's the subproof that justifies that formula. Okay, so let's look at a formalization of that rule. So if on line M we have an assumption that phi, and on line N, at the end of this subproof, we have phi, then on line 0, we're justified in writing phi, then psi. So in other words, in order to introduce phi then psi, we need a subproof going from the assumption that phi to psi. So our justification will be m to n conditional introduction. And notice that, again, we're always going to have this kind of structure to our justification. Just as in the other rules, where we've, in our statement of the rule, we refer to either one or two lines, it means that whenever we use that rule, we're always going to have to refer to just one or both, two lines. In this case, we're always going to have a range to look over. Okay, so let's look at that rule in action. So here we have a sequence A then B, B then C, C then D, therefore A then D. And this is really expressing some kind of transitivity relation. If A implies B, B implies C, and C implies D, then A implies D. And we're now in a position to show that A then D is derivable from these three premises. And we're going to go about it in much the same way that we did with our other proofs. So we'll begin by putting our conclusion on line Z. So that's going to be A, then D. And now I can ask, what do I need, or what would have I used to introduce this? Well, it's going to be a conditional introduction rule. And I now know from our conditional introduction rule that what I need to introduce a conditional is a subproof that begins with, in this case, the assumption that A, so I'll write that that's an assumption on line 4, and ends with our consequent D. So let's label that line Y. We can fill in the justification for this conclusion, 4 to Y conditional introduction. Now we can go about business as we did when we just had one scope bar. So we can think, how did we arrive at D? And we can look at our premises and think, well, we've got a conditional here, C then D. So if we could have the antecedent of C, then we could derive D here. Notice though, if we go back to our rule for conditional elimination, that as I said at the beginning, the conditional statement and its antecedent need to be on the same scope bar as the formula that we're deriving. So in the case that we're looking at now, with C then D being on this primary scope bar on line 3, that's not much use to us in this subproof. So what we're going to need to do is reiterate it. So C then D, and that's a reiteration from line 3. And we'll put that on line X. And above it, on line W, we're going to have C. So D is justified by W, X, and a conditional elimination. And now we can repeat the process. So we need to get C. We've got C as the consequent of this conditional, so if B, then C is on this line as a reiteration of line 2. And if we have B, then we can derive C. How are we going to get B? Well, B is the consequent of that conditional, so if we reiterate A, then B from 1, and we had the antecedent A, which we do because that's our assumption, then we can derive B. So now we can fill in our numbers 5, 6, 7. And swap out where we didn't justify it here. So B is coming from 4 and 5 and a conditional elimination. C is from 6 and 7 and a conditional elimination. 10 is from 8 and 9 and a conditional elimination, and then this is 4 to 10 and a conditional introduction. And there we go, it's really that simple to apply this rule. Just in order to introduce this conditional, we just need this scope bar going from the antecedent. It begins with the assumption of the antecedent and it ends with the consequent. Okay, so let's look at another example. We can introduce more than one subproof, and we can have a subproof within a subproof. So to demonstrate that, let's look at this particular sequence. A, therefore D, then C, then B, then A. So again, at the bottom, Z, I'm going to write our conclusion. D, then C, then B, then A. And I'm going to do the same thing that we usually do and ask, how could I have gotten to this? Well, looks like it was a conditional introduction, that's the main operator, from a subproof that will have begun with the assumption that D, that's on line 2, and finished with this consequent. So C, then B, then A. And that's going to be on line Y. So 2 to Y and the conditional introduction is our justification for this. Okay, then how did we get this? C, then B, then A. Well, again, it's going to be through a conditional introduction, and we know that for that we need a subproof that begins with the assumption of the antecedent. So the antecedent here is C, and that's going to be line 3. Again, we'll mark it as an assumption, and ends with the consequent, which is, in this case, B, then A. We'll say that that is line X. So our justification for this is 3 to X, conditional introduction. Once again, we can say, how did we get this? Well, conditional introduction, we're going to need a subproof. It begins with the antecedent, so the assumption that B, and it ends with A. So for how are we going to get A? Well, we already know that A is the case. That was one of our premises, so we can just reiterate that. And there we go, that's the end of our proof. So we've got 3 subproofs all kind of embedded. The first one from D to C, then B, then A requires these other 2 in order to fill it in. In fact, let's just write in our numbers. So B then A came from 4 to 5, this was 3 to 6, and this was 2 to 7. And there we go, that's our proof completed. So that's it for the conditional introduction rule. Now we'll look at the biconditional introduction rule. And remember, there's a quite close relationship between the conditional and the biconditional. So let's look at how the biconditional rule works by examining that relationship. So we've said before that a biconditional is really another way of saying these 2 formulas. So A if and only if B equates to something like A then B and B then A. So we should be able to derive A if and only if B from this premise, A then B and B then A. And let's have a look at how we might go about doing that. Well, the way that we justify a biconditional is just to have the justification for these 2 conditional statements. A biconditional is a conditional that goes both ways. So in the same way that for a conditional statement we have an assumption leading to the consequent, and that allows us to introduce the conditional statement, with a biconditional, if we have a subproof going the other way, then we can use both of these as justification for our biconditional statement. So in order to get to our conclusion of Z, A, if and only if B, we're going to need two subproofs, one that goes from A to B and one that goes from B to A. Now let's unpack our first premise a little bit first. So on line 2 we can have A, then B, and on line 3 we can have B, then A. In each case that's just going to be a conjunction elimination. Now we're in a position to write our two subproofs. So the first one is going to begin with the assumption that A, and it's got to end with B. Well, where might we get B from? Well, we've got this nice conditional here that has B as its consequent and A as its antecedent. So, if on line 5 we reiterate that statement, A then B, and that's a reiteration of 2, then we can derive B. So 4, 5, and a conditional elimination gives us B on line 6. Now we can just reverse that process for our next subproof. So this subproof has got to begin with the assumption that B, it's an assumption, and it's got to end with A. And again we've got this conditional statement, so if we reiterate it here, A, and again we've got this conditional statement here, B then A, so if we reiterate that here, then we can use line 7, which has got the assumption that B, and line 8, which has this conditional, to derive A on line 9. 7, 8, conditional elimination. And then we can renumber this 10, and we've got our justification for our biconditional. So we'll have to state 4 to 6, 7 to 9, and biconditional introduction. So it's just an extension of the conditional introduction rule. Let's have a look at a formal statement of it. So, if we begin on line M with an assumption that phi, and on line N we have psi at the end of that subproof, then on O we have a new subproof that begins with an assumption that psi, and on line P ends with phi. Then on line Q we're justified in writing phi if and only if psi, and the justification we give for that is M to N, O to P, biconditional introduction. So as before with the conditional rule, we've got this range of lines being cited, and we're always going to have to do that for the biconditional, so M to N, O to P. Notice that in both cases, so the biconditional and the conditional introduction, we have subproofs, and then the formula that's being introduced comes on the scope bar immediately to the left of those subproofs. So it doesn't occur on the subproofs themselves, it's immediately to the left. Look again, you can see the same thing happening in the conditional introduction rule. In order to justify this on one scope bar, we need a subproof immediately to the right of phi then psi. But again that means that the formula phi then psi always comes on the scope bar immediately to the left of that subproof. Okay, so let's look at two more examples in which we make use of subproofs. So here we've got the sequence A if and only if B, therefore A then B and B then A. And this is you can see the reversal of the sequence that we proved up here. So here we had A then B and B then A, therefore A if and only if B. So we should be able to derive this formula from A if and only if B as well. So we started with our premise, A if and only if B, and we're working towards having... So we'll start off with A if and only if B as our premise on line 1, and we can put in our conclusion A, then B, and B, then A, on line Z. And we know that this is going to have come from a conjunction introduction, and it's going to be a conjunction of A then B and B then A. Now I'm going to work down from the top here. We know that this is what we're going to be working towards, having A then B and B then A, and that's going to involve having two subproofs. So our first subproof is going to begin with A, begin with the assumption that A, and it's got to get down to B, and that will justify us in writing A, then B, and our second subproof has got to go from the assumption that B to A, and that will justify us in writing B, then A. So let's say that this is line Y, X, W, V, and U. So something's got to happen in between here. So on this subproof we need to get from A to B. How might we do that? Well, we've got this biconditional statement here. So, as we know from our biconditional elimination rule, if we have a biconditional and one side of that, we can derive the other. So if we reiterate that here, on line 3, A if and only if B, that's a reiteration of 1, then we can derive B. So U will become line 4, and 2, 3, biconditional elimination gives us B. So, we can renumber some of this now. On line 5 we get A then B, and the justification for that is 2 to 4 conditional introduction. Okay, so 6 we have B. Again, if we reiterate on line 7 this biconditional, A if and only if B, then we can use that to derive A. So 6, 7 and a biconditional elimination give us A, and that's going to be, in fact we can fill in the whole lot now, line 8. So on line 9 we get B then A, and our justification for that of course is 6 to 8 conditional introduction, and then 5 and 9 conjunction introduction finishes off our proof. So there we go, just using subproofs in a very easy fashion to get from A if and only if B to A then B and B then A. Okay, let's look at this final example then. So here we have a sequence of B or C, then not D, not D if and only if F, therefore B then F and C then F. So let's begin as usual by writing our conclusion on line Z, B then F and C then F, and then thinking about how we'd get this from these premises. Well, this is going to have come from a conjunction introduction. So above here we're going to need C then F, and this conditional of course is going to come from a subproof that begins with C, begins with the assumption that C, ends with F, and then we're also going to need B then F, and that too is going to come from a subproof which begins with the assumption that B and ends with F. let's just start working through. So that was an assumption. So if we have B, what can we do with this in order to get to F? Well, F is one half of this biconditional. So if we can get not D, we can derive F. And if we can get not D, we can derive not D. So what we really need is B or C. Now, of course, we can introduce that on line 4 with a disjunction introduction. So there's the antecedent of this conditional. Now, of course, we can't make use of this conditional yet because it's on a different scope bar. So on line 5, let's reiterate our conditional statement. B then C, B or C, sorry, and then not D, and that's a reiteration of 1. Now, on line 6, we can use lines 4 and 5 to derive not D. So that's 4, 5. Conditional elimination. Use the antecedent of this conditional here to derive its consequent. Now that I've got 6, I can get rid of these negations so that I'm left with just not D. So 6 and negation elimination gives me not D. So now, in order to get F, I just need to reiterate this biconditional. So on line 8, I'll write not D if and only if F, and that's a reiteration from line 2. Okay, so there's the first subproof, B to F. So F is justified, on line 9 by 7, 8 biconditional elimination, and on line 10 I get B then F, and the justification is 3 to 9 conditional introduction. Okay, on to the second one. So C we start off with, that's line 11. Again, we need something very similar, right? And remember that with our disjunction introduction rule, if we start off with phi, we can introduce another formula that comes before phi. So, come down here, we can just introduce B or C in exactly the same way. We can just repeat this part of the proof now here. So 12 would be, sorry, this is an assumption, we would have 11 disjunction introduction. We're going to need to reiterate, again we're going to need to reiterate this conditional. Even though we've got it here, we're going to need to rewrite it on this scope bar, because nothing from this scope bar can come onto this scope bar. It's confined to its own subproof. So here I can write B or C, then not D. That allows us to write not D. Sorry, that's a reiteration of 1, isn't it? Reiteration of 1, 12, 13, conditional elimination. Then on line 15 we can write not D by doing a negation elimination on that. Line 14. Then if we reiterate again our biconditional statement, not D if and only if F from line 2, then we can use lines 15 with not D and line 16 with that biconditional to derive F with the biconditional elimination. So then on line 18 we can see now that that's our conclusions on line 19. On line 18, C then F is justified by 11 to 17 conditional introduction, and our final formula, B then F and C then F, is 10 and 18 conjunction introduction. And there we go, there's our proof completed. So just one final thought about reiterations, actually. Let's move down to a second proof. Suppose we have a proof that begins with A as a premise, and then immediately goes to a subproof that begins with the assumption of A, then Z. Now, if we reiterate A from line 1, then we can use this A then Z to derive Z on this subproof. So that would be 2 and 3 conditional elimination. We can't now do any. Z cannot pass from this side of the subproof to the other, right? So we couldn't reiterate Z here. Okay, that's not allowed. The only thing that we could do, plausibly, is extend this a little bit. We could have if A then Z, then Z. And that's what follows here. That's what's derived from just A. So when we're reiterating, we can always reiterate from left to right. So anything on a left-hand scope bar, we can reiterate into a subproof to its right, and to subproof. So if we had another proof here, that began with A, or let's say began with B, we could again reiterate A there. But you can't reiterate the other way, so you can't reiterate that way round from a subproof back onto the proof. We can only use a rule to get things from a subproof onto our main scope bar. So that's just something to bear in mind about the way that reiteration works. Okay, so that's it for this week's session. Next time we'll look at introducing 2 more rules for some really sophisticated and slightly more complicated proofs.